Hello and welcome back to Introductory Electromancy. In this episode, we will be learning about capacitors. Your friend, the capacitor. Now, what is a capacitor? Capacitors come in many shapes and sizes. I'm going to be using multi-layer ceramic capacitors and aluminum electrolytic capacitors as my demonstration for this. These are both very common types of capacitor with somewhat different properties. Behold, the capacitor. These are charge storage devices. They have two electrodes with a high surface area between them and are able to store energy in the form of an electrostatic charge. This one is 220 microfarads, rated at 16 volts. Note that that is microfarads, F-A-R-A-D-S. Unfortunately, capacitance is not moderated by tiny ferrets inside the capacitor, as one might otherwise tend to believe. Now, this electrolytic capacitor has a stripe on one of the terminals, this right here, and looking at the lead wires, you can see that one is longer than the other. The longer lead wire is the positive terminal, and the shorter lead wire, the one connected to this stripe that has minuses written on it, is the negative terminal. Because of the way this capacitor is constructed, if you wire it backwards, it will explode out of this little perforated vent at the top that is designed to allow it to explode less catastrophically than if it did not have such a vent. I should say scored, not perforated. These things have a liquid electrolyte usually, and so it's necessary for them to remain completely sealed. So, electrolytic capacitors have a high capacitance per unit volume compared with other types, and have to be connected one way specifically in the circuit. This is in contrast to non-polarized capacitors, such as this multi-layer ceramic capacitor, which can be connected either way in the circuit. However, it has a smaller amount of capacitance per unit volume. Now let's look at the symbol, the schematic symbol, and the construction of some common types of capacitors. A non-polarized capacitor has a symbol which is composed of two identical horizontal lines, as shown. A polarized capacitor has one straight line and one curved line, with a plus indicating which side of it has to be connected to positive so that it does not explode or catch on fire. And/or. Note that these are not the only two capacitor symbols in existence. There are a wide variety of them. These are the two that I'm going to be using here. So, a capacitor stores charge, but what is it? How does it work? How do these wondrous devices function? Well, let's start by imagining a parallel plate capacitor. It has two large parallel plates separated by some sort of insulator. There are electrical connections to each of these plates. Suppose we connect a battery in series with it, like so. The negative terminal of the battery will produce a current of electrons. Which will flow along this wire here and build up on this plate. This plate of the capacitor will now have excess electrons. Because like charges repel, the electric field from these electrons will push away some of the electrons that are in the other plate because they are close to each other, leaving a net positive charge. Another way to visualize this is that it will cause there to be an electric field running through this thin layer of insulator called the dielectric. Very exciting, yes. But what do we use this field for? Well, here's where it begins to have practical applications. If we disconnect the battery after having charged the capacitor will still have the same internal condition: positive charge on this plate, a negative charge on this one, and an internal electric field through the dielectric. This can then be connected to a load. If we then attach the capacitor to a resistor, the excess electrons here will be able to flow through the resistor back around to the other plate. This means that the capacitor can be charged up, store energy inside of itself, and then discharged through a load. You'll run into capacitors in a wide variety of modern electronics. They are what is responsible for how oftentimes indicator LEDs do not immediately turn off as soon as you turn off or unplug a device. Instead, you see the indicator LED slowly fade to darkness instead of doing so in an instant fashion. That slow fade is the residual charge in the capacitors discharging through the indicator LED. Now, internally, ceramic capacitors are built just like this. There will be a thin layer of insulating material, and then two conductive plates of some kind, allowing an electric field to be induced between the two plates through the insulating material, storing energy. Let me get my visual aid here. Behold, a ceramic capacitor. This one is a multi-layer ceramic capacitor, so internally it'll actually look more like this, with interleaved fingers with insulation between them in order to increase the surface area between the two plates. To increase something's capacitance, you want surface area. You want that to go up. The more surface area, the more capacitance. And the thickness of the dielectric, the insulating layer, needs to be as thin as possible. the closer these two plates are together, the more a charge imbalance in one can affect the charges that are in the other plate. So a thinner dielectric gives you more capacitance, and a greater surface area between the plates gives you more capacitance. Now, these aluminum electrolytic capacitors are formed using aluminum and an electrolyte. I mentioned previously that aluminum is always growing a thin layer of aluminum oxide on it when it's in atmospheric oxygen, providing a clear, non-conductive layer, which is convenient for this application. It's also why aluminum house wiring can cause issues if you connect it to a not appropriately rated connector, because as the connector and aluminum wire expand and contract with thermal cycling, it forms a tiny gap which is exposed to the air, and then the aluminum grows a protective oxide layer which is non-conductive, so the resistance at that connection begins to increase. And because P equals I squared R, if you increase R, then the power dissipated increases, and anyway, it overheats the connector and burns down your house. So if you have aluminum wiring, make sure that you are connecting it to screw terminals and wire nuts and whatnot that are all specifically rated for aluminum wiring, or you'll have a bad time. Be very sad. So aluminum is always growing this very thin oxide layer. Suppose we take a sheet of aluminum and we electrochemically etch it so that instead of a smooth finish, it has a jagged finish. This increases its effective surface area. Then, if we put it in some sort of electrolyte, sometimes water-based, sometimes not, sometimes solid, solid electrolytic capacitors tend to last longer than water-based ones, but have worse properties in other areas. However, regular water-based electrolytic capacitors like this one will tend to dry out within 10 years or so, between 2 and 10 years, depending on a wide variety of factors. That said, if you put some electrolyte here and then connect it to the negative terminal of this whole device, connect the aluminum to the positive terminal of the whole device, the aluminum will grow a thin layer of oxide, which is non-conductive, on top of the ragged surface which you have already produced by electrochemical etching, and this forms a capacitor, because the electrolyte is one plate, the aluminum is the other plate, and the dielectric is the aluminum oxide, which has formed in a layer around the aluminum electrode. The upshot of all of this is that you can have crazy high surface area, because this thing has a sponge-like surface, and also a very thin dielectric because it is grown directly on the aluminum itself, perfectly matching any contours, topography, what have you. The only problem is that if you reverse the plus and minus, then it breaks down this layer and begins conducting large amounts of current and explodes and or catches on fire, depending on the exact electrolyte used and how badly you have applied too much power to it. Now, this description here with the electric field is the electrostatic explanation of how a capacitor works. It is partially true in that you can make a capacitor with a vacuum as a dielectric, where you just have one usually cylindrical shaped electrode and then another one outside of it, but barely not touching it. This is a cutaway view, I suppose. And if you put them inside of a glass container and evacuate it, you will have a capacitor that functions depending on the area between these two electrodes. However, there's more going on to the way in which a capacitor stores energy. Different materials have different dielectric constants. Now, it's definitely true that the movement of charge carriers on the plates and the electric field induced, that does store energy. But sticking different things in between the two plates alters how much energy can be stored. And that is because the material in between the two plates, called the dielectric, well, at room temperature, let's say you have some sort of polarized molecule that has a partial charge in one part of the molecule and a partial opposite charge in a different part. And this is a non-conductive thing that is put between two plates of a capacitor. And then if you apply a voltage to the plates, what happens is the atoms of dielectric are all twisted to line up with the applied voltage. The relative amount of polarization of the atoms comprising the dielectric, how much they twist, how much they want to return to their base state, is what is responsible for the differing dielectric constants of different capacitors. So, in summary, non-polarized capacitor has this symbol. A polarized capacitor has this symbol. Polarized capacitors always need to have the positive voltage applied to one terminal. Non-polarized capacitors are symmetrical. You can apply voltage either way, and it will still work. Now let's look at a practical application. I sure love practical applications. I'm going to take this LED circuit we've been using and rewire it. Guess this will be the first episode where I need more than one sheet of paper. So I'm going to make a circuit here, which will be a battery, a switch, which will actually just be me connecting and disconnecting the wire because we are very fancy here. 1 kilo ohm resistor, a red LED, and then a polarized electrolytic capacitor. going to be using this demo capacitor, which is 220 microfarads, rated for 16 volts. Generally speaking, you should not run your capacitors at more than half their rated voltage. 9 is already more than half of 16, so I am disobeying my own advice here. Also, I see that I have the 1 kilo ohm resistor in the schematic connected to the positive rail, but on what I breadboarded before, it is connected to the negative rail. It would work, but in the interest of accuracy, precise matching, I'm going to connect them exactly the way the schematic is, so that you, dear viewer, are able to closely follow this. So now we have our polarized electrolytic capacitor, and it goes with one lead connected to positive and the other connected to negative. The negative lead has this marking on it. So now what happens? Well, we still haven't attached our battery, but when we do, current will flow, lighting the LED, and this capacitor will become charged. The charging of the capacitor will be virtually instant in this application. It's limited by the internal resistance of the battery. If these were ideal components, there'd be an infinite spike of current when I close this switch, but the real world is not an ideal place. I'm sure you are shocked, truly shocked to hear this. Let me connect to the negative terminal. And the positive terminal. So you see the LED has become illuminated when current is applied from the battery, when voltage is applied, when current flows from the battery. My apologies. And then if I disconnect it, instead of going off immediately, the LED slowly gets dimmer. Let me give you a comparison without the capacitor so you can see the difference. Without capacitor, with capacitor. Gradual decay of charge. Now, a handful of things I wanted to mention here. Because a capacitor is just two conductive things separated by a non-conductive layer, our good old PN junction from our previous learnings, which has the non-conductive depletion region or depletion zone between the two types of semiconductor where they connect, where they touch each other. Well, it is a capacitor. You've got your dielectric here and two plates. But since applying a voltage can change the thickness of the depletion zone, you can actually change the effective capacitance of a PN junction diode by changing the amplitude of this voltage. Drawing an arrow crosswise through a component means that it is variable. For example, here is a variable resistor. Here is a variable capacitor. And here I was drawing a variable voltage source. In any case, varying this voltage changes the thickness of this depletion region, which changes the effective thickness of the dielectric of this capacitance. And so you can have a voltage-controlled capacitor using a PN junction. Diodes specifically made for this purpose are called varactor diodes. However, any PN junction will exhibit this effect. Now, regarding this circuit and its charge and discharge properties. A capacitor has a characteristic charge curve and a characteristic discharge curve. Let me start by describing the discharge curve. This axis will be voltage. I've already got it backwards. This axis will be voltage. This axis will be time. For a capacitor, which is discharging through a resistor in a circuit such as this one, poorly drawn arrows for my current. My oh my. That seems more legible. If the capacitor is discharging, it's going to have a discharge curve that looks like this. Starting off, quickly going down, and then gradually tapering off. The actual equation for this will be the capacitor voltage equals the initial voltage times E raised to the negative T over RC. E is Euler's number 2.71828 about. This is an exponential decay function. This comes from the solution of a first-order linear differential equation that describes the way that the current and voltage in capacitor circuits operates regarding calculus, but I am assuming that you are in introductory algebra for this, so getting to differential equations might be kind of a heavy lift. However, if you, dear viewer, find yourself compelled to, there is an excellent site, Paul's Online Math Notes, which will take you from algebra through calculus 1, 2, and 3, and differential equations. This would be after you get through the cartoon guide to algebra and the cartoon guide to calculus. Or if you are using only online resources, you could start here at algebra time. However, I only use these notes for calculus 3 and differential equations, so I don't know about the quality of the earlier ones. If the quality of the older ones is any indication, they're excellent. In any case, capacitor discharging. Now the equation for a capacitor charging, whatever the supply voltage is, times 1 minus e to the negative t over RC. That gives you a curve that looks like this. Where this is voltage and this axis is time. So capacitor discharging is up here. This is capacitor charging. And this term, RC, is called the time constant of the resistor-capacitor circuit. So making R bigger makes the time constant longer because there's a higher resistance, so current flows more slowly. Making the capacitor bigger gives you a bigger capacitance, which takes more time to discharge through R if it is the same size. I think that's about it for now. Next time, inductors.